So the first section is the geometrical optics, the second one is the physical optics, and of course the third one is sound. The course title is Basic Optics and Sound. Basic Optics and Sound. So I will be taking the first part, thereafter other lecturers will join. Now the first major thing that we are going to look at is light. And under that we are going to look at reflection and refraction of light. Now before we proceed further, light is a form of energy. It's a form of energy because plants, vegetables, they need light for them to grow. So when light is incident on some metals as well, they emit some electrons. So in that case, it means that light is a form of energy. Now, when you are talking of light, it is also in the visible part of the electromagnetic spectrum. In the electromagnetic spectrum, you have in the order of decreasing wavelength, you have the radio wave, you have the microwave, you have the infrared, and of course the visible light. That's where light belongs. After visible light, you have ultraviolet rays, you have X-rays, and of course you have gamma rays. So it is in the visible part of the electromagnetic spectrum. And when you are talking of light now, you can have red light or violet light. So for red light, the wavelength is about 400 nanometers. Sorry, for violet light, the wavelength is about 400 nanometers, and for red light, it is about 700 nanometers. So light can propagate through materials such as water, glass, and of course it can also pass through a vacuum. Materials that allow light to pass through them are called transparent materials. An example is glass that I just mentioned about, and even water. Those that do not allow light to pass through them, they are called opaque substances. Those ones, they disallow light energy to pass through them. Now, then that takes us to ray and beam of light. A ray is just a direction in which light energy travels, and of course rays are represented by arrows. As you can see, if you have a straight line indicating the movements of light rays, so it begins from a source, then indicating where it's going. So the arrow indicates exactly where the ray is heading to. So a ray is just a line drawn in the direction of propagation of light. And of course, when you have more than a ray, then it becomes a beam. So if you have 2, 3, 4 rays, then that one you don't call them rays, you can then refer to them as beam. So in vacuum, for example, in uniform medium, ray is a straight line, but that does not mean that it cannot bend. So in the medium, if the medium is not uniform, for example, at a surface, ray can be curved or bent. So you can have it as a straight line, you can have it as a curve or a bent ray. Now, a beam is a group of rays of light emitted by a source. And as I said earlier, when you have more than one ray, then it becomes a beam. Now, let's go to reflection of light. Reflection of light is the change in direction of light after hitting the surface. So, or throwing back of light ray when it strikes an obstacle. And the nature of the surface of the obstacle determines the type of reflection that occurs. Basically, we have two types of reflection. You have the regular reflection, you have the diffuse reflection. Regular reflection, in that case, it occurs when light strikes a smooth, plane surface, like a mirror. And in this case, what happens is that the beam is reflected in one direction. The beam is reflected in one direction. Unlike in the case of diffuse reflection, when light strikes a rough surface or a non-mirror light surface, such as a clothing material or a sheet of paper, you have the beam being reflected in different directions. So as you can see in this slide, on this slide you have regular or specular reflection. So you have a beam. In this case, you have about 5 rays. So the incident beam gets into a smooth surface and reflected back in one direction. Unlike in the case when it hits a raw surface, where you have diffuse reflection, you have the incident beam, and of course the reflected rays are scattered. So when that happens, you call it a diffuse reflection. So diffuse reflection occurs when the incident ray or the incident beam hits a rough surface. A regular or specular reflection occurs when the incident beam hits a smooth surface. Before we progress, let me also tell you that in the case of beam, you can have a divergent beam, you can have a parallel beam, and of course you can also have a convergent beam. A very good example of convergent beam is the one that you have from a projector. So when the projector is, you can see that it's focused on the screen, so it gives you a convergent beam. Then in the case of parallel beam, a very good example is when you have your torchlight. If you on your torchlight, it gives a parallel kind of light. So because of that, you can see from afar. Then the rays from the sun is also substantially parallel. The rays from a distant object such as the sun is also very parallel. Then in the case of divergence, a very good example is when you put your lamp, you on your lamp and you put it, you can see that the ray diverges from the initial position. So we have been able to define reflection as change in direction of light after striking or hitting the surface. Then that takes us to the laws of reflection. There are basically two laws. The first one is the incident ray. The reflected ray and the normal are in the same plane. The incident ray, the reflected ray, and the normal are in the same plane. And the second one is that the angle of incidence is equal to the angle of reflection. As you can see from here, you have the incident ray making an angle theta I with the normal. Then you have the reflected ray making an angle theta R with the normal. So the incident ray, the reflected ray, and the normal are the same. The incident ray, the reflected ray, and the normal are in the same plane. So what you have here is the plane. You can see that the incident ray gets to a plane. Then you also have the normal, and the reflected ray is also on the same plane. That tells you what the first law is all about. Then the second law is basically saying that theta I equals to theta R. In other words, the angle of incidence is equal to the angle of reflection. That is the second law of reflection. That is the second law of reflection. Now let's look at reflection at plane surfaces. Reflection at plane surfaces. A mirror is a highly reflecting optically smooth surface. A mirror is a highly reflecting optically smooth surface. For example, a highly polished silver surface. A highly polished silver surface. So a plane mirror then is a plane reflecting surface. A mirror is a highly reflecting optically smooth surface. Then a plane mirror is a plane reflecting surface. Then we can then go ahead and look at the images or the type of images that are formed by a plane mirror. If you see this figure is showing a plane mirror. You have the reflecting surface, you have the eye on one side, facing the mirror. Then on the other side, you have the image that has been formed. There can't be image without an object. So this is the object. You have an object, then the image is formed on the other side of the plane mirror. So the characteristics of the image formed by a plane mirror, number one, the image is the same size or is of the same size as the object. As you can see, the image here is the same size as the object that is located on the other side of the plane mirror. So the image is the same size as the object. That is the first characteristic. The second one is that the image is far behind the mirror as the object is in front. So you have the object in front, then the image is behind the mirror. Then the third one, the image is virtual, that is, cannot be formed on the screen. Since the plane mirror, you cannot get the object on the plane mirror, but it looks as if it's at the back of it. So in that case, the image is said to be virtual. Then number four, the image is erect. As you can see, the image is as sharp as the object. Then that takes us to reflection at spherical or curved surfaces or mirrors. Reflection at spherical or curved mirrors. Spherical mirrors are shaped like sections of a sphere and may be reflective on either side of the mirror. In the case of a concave mirror, the reflective side is inside. In the case of a concave mirror, you have the reflective side to be inside. Then in the case of a convex mirror, the reflective side is outside. So concave mirrors are mirrors that use the inside as their reflecting surfaces. And of course, convex mirrors use the outside as their reflecting surfaces. Take note of that. They are not exactly the same thing. So in the figure that you have on this slide, you have a convex mirror. As you can see, the outside is where the aperture is. As we progress, we talk about the aperture. So the outside is where the reflecting surface is. And in the case of the concave mirror, normal to the surface, the reflecting surface is actually inside the mirror. So in the case of a concave mirror, the reflecting surface is inside and not outside like that of the convex mirror. There are some basic terms that we need to talk about when talking about spherical mirrors. There are some basic terms that we need to talk about, we need to define. The first one, and I'm very sure you are familiar with this, the first one is the principal axis. The principal axis is the line joining the pole and the center of curvature of the spherical mirror. The principal axis is a line joining the pole and the center of curvature of the spherical mirror. The principal axis is always a straight line that is at the center of the mirror. Excuse me. So the next one is the pole. But before we progress, if you look at the principal axis, the pole is actually the center of the mirror. So the straight line that gets to the center of the mirror and does not bend is called the principal axis. It's actually called the principal axis. Then the pole, which is denoted by P, is the geometrical central point of the reflecting surface of the mirror. And of course, in the pole, you can get the aperture, which is the width of reflecting spherical surface. So in the aperture, there can be reflection. There can be reflection in the whole, in the entire sphere of the aperture. That's why it is called aperture, because the reflection can actually take place from there. Then you also have the center of curvature. The center of the hollow sphere, of which the mirror is a part, is actually called the center of curvature. So the center of curvature is denoted by C in the next figure. The center of curvature is denoted by C. So that is the center of curvature. Then the next one is the radius of curvature. The radius of curvature is just the distance between the pole and the center of curvature. So that gives you PC. If you look at the figure, P is the midpoint of the mirror. So the distance between P and C is the radius of curvature. Then the focal point, or what is also called the principal focus, F. F is the focal point. It is also called the principal focus. So it is the point on the principal axis where all parallel rays meet after reflection. As you can see in this figure, all the rays, by the time they have reflected back, they have to meet at the focus. The focus is capital F. The focus is given by capital F. Then you have the focal length, which is the distance between the pole and the principal focus. So PF is the focal length and is given by small f. Is given by small f. Now, there is a relationship between the radius of curvature and the focal length. F equals to R over 2. That means your R equals to 2F. R is the radius of curvature. F is the focal length. That is a very good relationship between them, which we'll be using for solving some problems under this particular subject. So F equals to R over 2. F is the focal length. R is the radius of curvature. Now that will take us to formation of images by spherical mirrors. Formation of images by spherical mirrors. There are rules here. There are 3 key rules that we need to follow. The first one, when a ray parallel to the principal axis, what happens after reflection? Then the other one, when the ray through the focal point after reflection, what happens? And of course the third one, when the ray through the center of curvature passes, hitting the surface of the mirror, what happens? In the first case now, a ray parallel to the axis after reflection passes through the focal points or through the principal focus. Now look at what is happening here. This is the principal axis. Then the ray, the next line here, we're indicating that arrow shows that the ray is parallel to the principal axis. Because if you can see the principal axis, and you see the next ray, so it's parallel to the principal axis. So after reflection, it passes through the principal focus. Now, this ray, after hitting the surface of this concave mirror, it passes through the principal focus, F. That is the first rule. And this is for concave mirror. In the case of the convex mirror, you also have a ray parallel to the principal axis, of course, passing through the focus behind the mirror. in the case of convex mirror. That's why you have all these dotted lines. So this is actually the ray parallel to the principal axis in the case of convex mirror. Then don't forget that the reflecting surface of the convex mirror is outside the mirror. So then the focus is behind. The focus is behind. So it passes through the focus and of course is reflected along that particular direction. Then the second one is that when you have a ray through the principal focus, after reflection, it is parallel to the axis. You have a ray. In this case, you have a ray for a concave mirror. This is the ray passing through the principal focus. After reflection, then it is parallel to the principal axis. So in the case of concave mirror, you have the ray with this arrow. Then it gets to point F, which is the principal focus. Then it hits the reflecting surface of the concave mirror. Then it is reflected back, and that reflection shows clearly that it is parallel to the principal axis. And in the case of the convex mirror, you also have the ray, which is through the principal focus. After reflection, is also parallel to the principal axis. But in the case of the convex mirror, the focus is behind. The principal focus is behind. Then for the third one, a ray of light which passes through the center of curvature will retrace its path after reflection. A ray of light which passes through the center of curvature will retrace its path after reflection. So what you have in this case is that you have a ray. This is the ray which passes through the center of curvature C and hitting the mirror. What happens in this case is that it will have to retrace its path. That's why you have a to and fro arrow. As you can see, this arrow pointing towards the reflecting surface. Then you also have the other arrow pointing in the reverse direction for a concave mirror. And of course, the same thing is applicable when you are talking of a convex mirror. But the only difference is that the focus, the center of curvature is actually behind. So those are the three rules in the formation of images for a concave mirror. Then let's go to image formed by concave or converging mirrors. Another name for concave mirror is actually converging mirror. Now, real images are formed if the object is beyond the focal point. Real images are formed if the object is beyond the focal point. In the next diagrams, we'll be looking at objects represented by AB and the images formed represented by B prime, A prime, B prime, A prime. So look at what happens here when the position of the object is at infinity. When the position of the object is at infinity, then the position of the image is at the focus. The position of the image is at the focus. Then the size of the image formed is that it is highly diminished and of course a point-sized image. That's why it is difficult for you to locate it at point F. Then the nature of the image formed is that it is real and inverted. It is real and inverted. So when the position of the object is beyond C, when the position of the object is beyond C, the position of the image is between F and C. As you can see in that diagram, the position of the image is between F and C, and the size of the object is that it is diminished. The size of the image is that it is diminished, and of course the nature of the image is that it is also real and inverted. It is real and inverted. When the position of the object is at C, when the position of the object is at C, then the position of the image formed will also be at C. The position of the image formed will also be at C. Then the size of the image is that it is of the same size. It is of the same size as that of the object. So take note of that. When the object is at C, the image is at C, then the size of the object is the same as that of the image. And of course, the nature of the image formed is that it is real and inverted. Real and inverted. When the position of the object is between C and F, when the position of the object is between C and F, the position of the image is beyond C, and of course it is enlarged, as you can see in the figure. This image is enlarged, and it is also real and inverted in nature. It is also real and inverted in nature. When the position of the object is at F, that is at the principal focus, the image is at infinity. The image is at infinity, and the nature of the size of the image is that it is highly enlarged. It is highly enlarged, and of course real and inverted. When the position of the object is between P and F, You have the image to be behind the mirror, and of course it is enlarged in size, and in this case you have a virtual and a red image. A virtual image is the one that cannot be formed on the screen, while a real one is the one that can be formed on the screen. Quickly, let's look at uses of concave mirrors. We have been talking of concave mirrors. Do they have anything that we can do with them? Yes, there are many uses of concave mirrors, and we have listed a few here. Number one, concave mirrors are commonly used in torchlights or searchlights and vehicle headlights. They are used in searchlights or torchlights and used also in vehicle headlights in order to be able to get powerful parallel beams of light. For you to be able to get powerful parallel beams of light, you make use of concave mirrors. Then the other use is that they are used as shaving mirrors. They are used as shaving mirrors to see a large image of the face. So the image, the nature or the type of mirror used for shaving is actually the concave mirror. The third one is that the dentists use concave mirrors to see large images of the teeth of their patients. The dentists use concave mirrors to see large images of the teeth of their patients. And the fourth one, they are also used to concentrate sunlight in order to produce heat in solar furnace. They are used to concentrate sunlight to produce heat in solar furnace. Then this one will take us to image formation by a convex mirror. We have talked about that of concave mirror. So what are the images that are formed by a convex mirror? In this case, we are going to consider two positions. The first one is when the object is at infinity, and the other one is when the object is at a finite distance from the mirror. When the object is at infinity and when the object is at a finite distance from the mirror. So in the two cases, for example, when the object is at infinity, what are the characteristics of the image formed? Number one, the image formed when the object is at infinity is that the image is formed at F. The image is formed at F. Then two, the image is highly diminished and of course point size image, a dot size image. The image is highly diminished, point size in nature. Then the image is virtual and red, that means it cannot be formed on the screen. And the fourth one is that the image is formed on the other side of the mirror. So when you have the object at infinity, those are the cases that you get for the image. Then when the object is at any point between infinity and the pole, the characteristics of the image formed include the following. Number one, the image is formed between P and F. The image is formed between P and F. Then the image is diminished in size, smaller than the object. Diminished in size, that means it is smaller than the object. Then the image is also virtual and red. Then is formed on the number four. It is formed on the other side of the mirror. It is formed on the other side of the mirror. So in the case of convex mirrors, we have looked at the images formed when the object is at infinity and when the object is also at the finite distance from the mirror. So they form different kinds of images. They form different kinds of images. In the case of convex mirrors, they are also used as rear view mirrors in vehicles. Those side mirrors that you see on vehicles, they are actually convex mirrors. They are actually convex mirrors. So they enable driver to see traffic behind in order to facilitate safe driving. So they are also very, very useful. Convex mirrors are also very, very useful. Then that will take us to a mirror formula and magnification, which I'm very sure you are familiar with. The formula has not changed. You have 1 over F equals to 1 over U plus 1 over V. You have 1 over F equals to 1 over U plus 1 over V, where F is the focal length, V is just the image distance, V is the image distance, and U is the object distance. U is the object distance. So we'll be using this formula to solve some problems as far as mirror or even lenses are concerned. 1 over F equals to 1 over U plus 1 over V. This is the mirror formula. What about magnification? Magnification is just the image distance given by V divided by the object distance given by U. Magnification, image distance V over object distance U, or it is, you can say it is image height over object height. Image height over object height, they are just the same. But there is something that we can bring out from the formula. Our formula, the mirror formula, is 1 over F equals to 1 over U plus 1 over V. Now, if we decide to multiply both sides of this formula by V, then your 1 over F equals to 1 over U plus 1 over V will then give you V over F equals to V over U plus V over V. V over V will give you 1. And don't forget that V over U is your M, is the magnification. So if you now make magnification the subject there, magnification M will give you V over F minus 1. Magnification M will give you V over F equals to 1. That means we have been able to generate another expression for magnification M. So it's either you say V over F minus 1 or V over U. So it depends on the parameters or the variables that the examiner will decide to give. So, but there are some things that we need to pick from here. When the magnification is greater than 1, when M is greater than 1, that means the image is magnified. In other words, the image is bigger than the object. When magnification equals to 1, when M equals to 1, then the image is of the same size as the object. The image is of the same size as the object. When M is less than 1, the image is diminished. In other words, the image is smaller than the object. Now, to conclude on this segment, there are two examples. Number 1, a man uses a concave shaving mirror of radius 30 centimeters. If his face is 10 centimeters from the mirror, find A, the position of his image, and B, the magnification. A man uses a concave shaving mirror of radius 30 centimeters. If his face is 10 centimeters from the mirror, find A, the position of his image, and B, the magnification. All we need to do here is just to apply the mirror formula. 1 over F equals to 1 over U plus 1 over V, 1 over F equals to 1 over V plus 1 over U. But in this case, it is the radius that is given. And don't forget that our F equals to R over 2. F equals to R over 2. So in that case, your R equals to 30 centimeters, which is the radius that is given, and U equals to 10 centimeters. We need to take note of something here. No negative signs because the mirror is a concave mirror. No negative sign for the object and even for the focus as for the radius or curvature because the mirror is a concave mirror. So our U equals to 10 centimeters. Our R is 30 centimeters. But what we need in the formula is F. So that will give us 2 over R. Your 1 over F equals to 2 over R. So if you bring in those values, you now have 1 over V equals to 2 over R minus 1 over U. So R is given to be 30. You now have it to be 2 over 30 minus 1 over 10. This will give you minus 1 over 30. In that case, your V equals to minus 30 centimeter. Your V equals to minus 30 centimeter, which means that the image is 30 centimeters behind the mirror. That minus sign indicates that it is a virtual image and it is 30 centimeters from or behind the mirror. So to solve B part, which is the magnification, from our expression M equals to V over U, our V is 30 centimeters, our U is 10 centimeters. So M equals to V over U equals to 30 over 10. That will give you 3. Take note that in the case of magnification, the symbols or the signs are insignificant. So that's why that minus 30 is not appearing here. In the case of magnification, you do not take cognizance of the signs. So magnification is 3. Magnification is 3, and it is not also in any unit because the units will have to cancel each other. The second example is the image of an object in a convex mirror is 4 centimeters from the mirror. The image of an object in the convex mirror is 4 centimeters from the mirror. If the mirror has a radius of curvature of 24 centimeters, find the object position and the magnification. If the mirror has a radius of curvature of 24 centimeters, find the position of the object and the magnification. Similar to what we did, but in this case, it is a convex mirror. Because it is a convex mirror, and we said that the reflecting surface is behind and the focus is behind, then it's going to affect the signs. So V is given to be 4 centimeters, but because it is a convex mirror, your V is now minus 4 centimeters. Your V is now minus 4 centimeters. Our F, the radius of curvature is given to be 24 centimeters. So since our F equals to R over 2, that will give us 24 over 2, which is 12 centimeters. 12 centimeters. But because it is a convex mirror, so your focal length F is now minus 12 centimeters. F is minus 12 centimeters. Minus 12 centimeters. And once you have been able to establish this, all you need to do is just to substitute straight away into the expression 1 over F equals to 1 over V plus 1 over U. So if you bring in those values, you have your 1 over U equals to minus 1 over 12 plus 1 over 4. That gives you 1 over 6. So U will then give you 6. In this case, U is positive in sign, so the object is real and it is 6 centimeters from the mirror. U is positive in sign, that means it has brought out a real object, and it is also 6 centimeters from the mirror. For the magnification, M equals to V over U. Our V is 4, our U is 6, so that gives us 2 over 3. 2 over 3, hence the image is 2/3 as high as the object. So that is the way to conclude it. It tells us that the nature of the image, comparing it with that of the object. In this case, you have it to be 2/3 as high as the object. We then talk of refraction. Refraction is another phenomenon when you are talking of light. Refraction is just the bending of light rays at an interface between two transparent optical media. Refraction is the bending of light rays at an interface between two transparent optical media. Now, in other words, refraction is just the change in the direction of light after passing through from one medium to another. We cannot talk of refraction without talking of the index of refraction, which is given by small letter n. Index of refraction is given by small letter n. Now, the two transparent optical media, in this case, light is passing from one medium to another. So you are not making reference to two media. If it is passing from one medium to another, that means you have two media involved. So the two transparent optical media that form an interface, they are actually distinguished from one another by a constant that is called the index of refraction, or refractive index, given by n. So n is defined as C over V. N is defined as C over V, where V is the speed of light in the medium. V is the speed of light in the medium, and your C is the speed of light in free space or vacuum. C is the speed of light in free space or the vacuum, and of course your N is the refractive index. Researchers have done many work, and they have come out with different values for various. They have come out with values for different materials for refractive indices. So you have them. You have for glass. You have for water. You have for ice. You have for silicon. You have for diamond, and so on and so forth. So these are constant values that the researchers have come out with. But one good thing here is that the greater the index of refraction, the lower the speed of light in that medium. The greater the index of refraction of a medium, the lower the speed in that particular medium. Don't forget that your N is actually defined by C over V. Then let's look at what happens when you have light moving from one medium to another. For example, moving from a denser medium to a less dense medium. Moving from a denser medium to a less dense medium. Then, of course, when it's also moving from a less dense medium to a denser medium. So what happens in the case of light moving from a denser medium to a less dense medium? When you have it moving from a denser medium to a less dense medium, is that there's a bending away from the normal. As you can see in one of the figures, the light bends away from the normal when it is moving from a denser medium to a less dense medium. For example, when it is moving from glass into air, from a higher to a lower refractive index, there is a bending away from normal. On the other hand, when you have it moving from a less dense to a denser medium, it bends towards the normal. It bends towards the normal. For example, when you have it moving from air into water, so there is a bending towards normal. There's a bending towards normal. Take note of that. Refraction also has its own laws as well, similar to that of reflection. So let's look at the two laws of refraction. Refraction also has two laws. The first one, the incident ray, the refracted ray, and the normal at the point of incidence all are in the same plane. The incident ray, the refracted ray, and the normal at the point of incidence all are in the same plane. That is the first law of refraction. The second law, which is also known as Snell's law, is the ratio of the angle of incidence is the ratio of the sine of the angle of incidence to the sine of the angle of refraction, and is given as a constant, which is also known as Snell's law. So in other words, it is sine I over sine R equals to n. It is sine I over sine R equals to n, which is the sine of the angle in the incidence for the incidence divided by the angle in the refracted ray. The refracted angle will give you n, will give you the refractive index. So those are the two laws for refraction. But we need to also say there's a formula here which we also use in our calculations. I've said earlier what happens bending away from normal and bending towards normal, bending away and bending towards normal if it's moving from a higher refractive index to a less one, and of course from a less one to a higher one. So you have this expression n1 sine theta 1 equals to n2 sine theta 2. What you have there, they are just n is the refractive index, or n1 is the refractive index of the surrounding air, n2 is the refractive index of a glass. In this case, n2 is the refractive index in the glass slab. Theta 2 is the refraction angle. Theta 2 is the refraction angle, and of course, theta 1 is the incidence angle. This expression is also important, so as we progress, we'll be talking about them. Then you also have total internal reflection and critical angle. Total internal reflection and critical angle. Total internal reflection is let me just explain it this way. When you have light moving from a denser medium to a less dense medium, there's always an increase. As the incident angle increases, the refracted angle or the angle of refraction also increases. When you have light moving from a denser to a less dense medium, the angle of refraction is always greater. So if you increase the angle of incidence, the refraction angle will also increase. So it will get to a level that you have a critical angle. That critical angle is the angle of incidence, and in that case, the angle of refraction will be 90 degrees. The angle of refraction will be 90 degrees. And from basic mathematics, you know that in each quadrant, you have 90 degrees. You have 4 quadrants, first, second, third, and fourth, and the maximum angle in each quadrant is 90 degrees. So what happens is that when it gets to critical angle in the angle of incidence, at that point, the angle of refraction will be maximum, will be 90 degrees. So any increase in the angle of incidence will then form what is called total internal reflection. So instead of the refraction or the angle of refraction increasing, it will then come back into the other medium, which will then give you total internal reflection and not refraction in this case. So total internal reflection occurs when light travels from a denser medium to a less dense medium, where the angle of incidence is greater than the critical angle. The critical angle is usually given by C. The critical angle, when it occurs, then the angle of refraction, the maximum is 90 degrees. So any increase in the angle of incidence, you then have what is called total internal reflection. You then have total internal reflection in the denser medium. So if you can see the sketch, you have N1. Then these arrows indicate that this is the interface moving from a denser medium to a less dense medium, N2. So N2 is N2 is less than N1. N1 is at a higher refractive index than N2. So you have the arrows. So when it gets here, as you increase the angle of incidence, the angle of refraction also increases. So when it gets to when the angle of incidence is critical, then the angle of refraction becomes 90 degrees. It becomes 90 degrees. So any increase in the angle of incidence will then form total internal reflection in the first medium, or in the denser medium. So that will give you sin theta equals to N2 over N1, and sin 90 degrees equals to N2 over N1. Sin 90 degrees, it will be 1. So there is always a formula, N equals to 1 over sin C, for relating critical angle and refractive, and the angle of refraction and the refractive index. So if the angle of incidence is larger than this, there will be no transmission occurs, there will be no transition, and what results is the total internal reflection. Basically, there are two instances, there are two conditions that must be met for total internal reflection to occur. Number one, light must travel from a denser to a less dense medium. Light must travel from a denser to a less dense medium. In other words, for example, if it is traveling from water then into air or glass, because the refractive index of air is 1, the refractive index of water is 1.33, the refractive index of glass is 1.52. That means glass is denser than water, water denser than air. So it has to be traveling from a denser medium to a less dense medium for total internal reflection to occur. Then the second one is that the angle of incidence must be greater than the critical angle. The angle of incidence in the denser medium, the angle of incidence in the denser medium must be greater than the critical angle C. Are there applications for total internal reflection? Yes, there are many. We have given a few here. They are used in optical fiber optics. They depend on total internal reflection. They depend on it to transmit light signals with very small losses. So they are used in optical fibers. They are used in telecommunications. The phenomenon of total internal reflection is also used in telecommunication, and of course used in the area of medicine as well, for correction of medical problems. They are used in medicine for correction of medical problems. So we'll end this first segment here today. By God's grace, next week we'll continue from there. Thank you very much for listening, and God bless.